Welcome back. This video is over exponential functions, which covers section 9.2. We're going to start talking about graphing exponential functions and what is an exponential function. So far, we've talked about y equals x squared, y equals x cubed minus 1. Now we're going to have what we call an exponential function, where you can see that the variable is in the exponent. An exponential function definition. Let b be a constant real number such that b is greater than 0 and b does not equal 1. Then for any real number x, a function of the form f of x is equal to b to the x is called an exponential function of base b. And exponential functions happen in the real world all the time. So like whenever COVID first happened, it was growing exponentially. And also bacteria grows exponentially. Okay, so for number 1, this says f of x equals 3 to the x power. I just want to point out that the 3 is called the base. And then of course the x is the exponent. And what we'll do is we're going to explore what this graph looks like by plugging in some values for x. All right, so we're just going to kind of get a general idea of what this graph looks like. Since this is greater than 1, this is also considered exponential growth. All right, so when I plug in 0, I get 3 to the 0 power, which is 1. 3 to the first power is 3. 3 squared is 9. And 3 cubed is 27. 3 to the negative 1 power is 1/3. 3 to the negative 2 power would be 1 over 9. And 3 to the negative 3 power will be 1 over 27. Okay, now let's graph this and see what happens. So I'll start with my ordered pair 0, 1. And just do your best. And then 1, 3. And so I'm just taking the ordered pairs from, these are my x's, right? And then here are my y's. Okay, so I'm just graphing each ordered pair. So 0, 1, 1, 3. Okay, 2, 9. 3, 27. And then this gets a little difficult to graph. But basically what happens is it gets closer and closer to 0, but it never crosses. So it has a general shape that looks like this. And really it looks like that. It's just kind of hard to graph on my iPad, but that's what we call exponential growth. All right, and notice that the base is 3, which is greater than 1. Okay, so let's talk about what happens when we have a base that is in between 0 and 1. So we're going to change this to our benefit. We're actually going to change it to 1/2 to the x power. Now there's a few things I want to point out. So just pretend that that's what the problem said initially. So 1/2 to the x power. The 1/2 is considered the base. Of course, x is the exponent. And since it's in between, since the base is in between 0 and 1, we call this exponential decay. Okay, so let's go ahead and explore what this will look like. All right, so I'm going to plug in 0. I'll do this in red. So 1/2 to the 0 power is just 1. 1/2 to the first power is 1/2. 1/2 squared is 1/4. 1/2 to the third power would be 1 over 8. And then 1/2 to the negative 1 is 2. 1/2 to the negative 2 is 4. And then 1/2 raised to the negative 3 power is 8. Now we're going to take our x coordinates and our y coordinates, and we're going to use each of these as ordered pairs. So 0, 1 would be my first ordered pair to plot our graph. So 0, 1 is about right there. 1, 1/2. 2, 1/4. Okay, you can see that it's really difficult to graph my fractions, right? So that's difficult, so just do your best. And then I've got -1, 2. That's a little easier, right? And then -2, 4. And -3, 8. Okay, so that general shape, or curve, I should say, looks like this. All right, so exponential decay has a general shape that looks like this, whereas exponential growth, looks like that. Okay. So for the parent function y equals 2 raised to the x power, we can actually use our transformations to help us with shifting and creating a new graph. So for f of x is equal to a times b raised to the x minus h plus k, notice that in the exponent is that horizontal shift left or right. And then, of course, the plus k is going to move it up or down. And then the a reflects it. And then we can have a vertical shrink or stretch depending on what that a factor is, right? Okay. Let's talk about evaluating the exponential function with base e. E is a universal constant like the number pi and an irrational number. We also call e the natural base. The reason why e is called the natural base is because it occurs in the sciences naturally all the time. Here is one way we can derive e. As x approaches infinity, the expression 1 plus 1 over x raised to the x power approaches a constant value that we call e. E is approximately 2.718281828, and actually the number goes on forever. It's probable that your calculator has the letter e on it. So you should look at your calculator and see if you can find the letter e. It will be useful in this section for sure. Okay, so we're going to evaluate. We're going to round to 4 decimal places. If you don't know where e is on your calculator, you can use this decimal to help you. So when I type in e squared into my calculator, which I would do with a calculator, I get approximately 7.3891. When I type in e to the -3 power, I get approximately 0.0498. When I do e raised to the square root of 7, I get approximately 14.0940. And when I do e to the pi, I get approximately 23.1407. All right, we're going to use exponential functions to compute compound interest. So one of the applications in this section has to do with money and compound interest especially. So there are a few formulas that we're going to talk about. The first is called simple interest. That is just I equals PRT, where P is the principal invested at an annual interest rate R for T years. We can also use a different formula if we are doing compounding amounts of money, or if we're compounding, if we have compound interest instead of simple interest. We'll use this formula, where A is the amount of money in the account after T years, and N is the compounding periods per year. And then we use A equals PE raised to the RT. I call this PERT. There is a shampoo. And that is whenever we're using continuous compounding. So those are the 3 different types of formulas we can have. So it says, suppose that $15,000 is invested with 2.5% interest under the following options: compounded annually and compounded continuously. Determine the amount in the account at the end of 7 years for each option. Okay, So if we're going to do compounded annually, we're going to be using this formula, and it helps to label everything we know. So the P is the principal amount. It's the amount we're starting with. N is the number of times it's compounded per year. They're giving us that. They're saying annually. Annually is once a year. T is the time in years, which is 7. And then R, our interest rate, is 2.5%. But I just want to go off to the side. We can't actually use 2.5%. We have to get rid of the percent. So to do that, you can move the decimal 2 to the left, or simply divide it by 100, which is 0.025. Okay, now I'm ready to plug it into my formula. So the amount of money I have over time would be equal to P, which is right here, and then I have parentheses 1 plus R, which is 0.025, over N, which is 1, raised to the 1 times 7. Now, I know that 1 times 7 is 7, but I'm just trying to show all of my work here, because sometimes we're going to have other numbers for N, like in this case for letter B, quarterly would change my 2 values to 4. Okay, now what I tell my students is to very carefully, I would type this entire thing into your calculator all at once. Use your parentheses, use your fraction key, use your power key, and I would give you a moment to do that. So you might try that in your calculator. And if you do it correctly, you should end up with approximately $17,830.29. All right, that is compounded annually. Now, we're going to talk about compounded quarterly, because, I kind of ran out of space. And then we'll talk about compounded, continuously. All right, which is letter C. Okay, so letter B, so we're finding now a new problem. We're going to figure out what about if it's compounded quarterly. Now, quarterly means 4 times a year. So if they said monthly, that would mean 12 times a year. So how does that change? What does that change? Well, we're still using the compounded interest formula, but this time our N will be 4. All right, so P is still 15,000. T is still 7. My interest rate is still 0.025, but this time N is equal to 4. Okay, now I'm ready to plug that into my formula. So the amount I'll have over a certain amount of time is equal to 15,000, 1 plus, and then I've got 0.025 over N raised to the N times T. Now I know that 4 times 7 is 28, and some people will go ahead and change that to 28. It's kind of up to you. I like for my students to try to get this whole thing into their calculator. I think it's good practice to be calculator savvy and just to type this all in at once. And if you choose to do that, make sure you use parentheses, make sure you use the fraction key, all that good stuff. All right, so you might pause the video and try it in your calculator. I'm going to go ahead and reveal what I got. So I got approximately $17,858.96. So when we think about money and interest, the more often that the interest is compounded, the higher the amount will be. So you can see a slight difference between our two answers. This was $17,830, while this is $17,858, right? And then the last one we're going to talk about for this type of problem is when it's compounded continuously. Continuously means to use E. So we are now going to be using the PERT formula, where we still have an investment of 15,000. So that's my P. My R is still 0.025. And then my T is 7. So I'm going to have 15,000 times e raised to the r times t. And once again, this operation here is multiplication. I would type this whole thing into my calculator. So you're really going to be looking for that E key on your calculator because you don't want to always have to use 2.71828. You're going to be looking for that E key. Now, if you do this correct, you should get approximately $17,868.69. That is even higher because compounded continuously means compounded at all times. All right, let's move on. All right, so here are some other type of application problems we can have. It says weapon-grade plutonium is composed of approximately 93% plutonium-239. The half-life of Pu-239 is 24,000 years. In a sample originally containing 0.5 kilograms, the amount left after t years is given by A at t equals 0.5 times 1/2 raised to the t divided by 24,000. Evaluate the function for the given values of t and interpret the meaning in the context. So for 24,000 years, which is kind of crazy, we're just going to evaluate the function at 24,000. So what we're going to do is we're going to take our 24,000 and we're going to plug that in to our formula for t. And you can see that what happens really with this exponent is that that's just going to become to the first power, right? Let me highlight that. So this will just be really 0.5 times 1/2 to the first power, which is just going to be 1/4. So that means that if we have a certain amount, 0.5, and the half-life is 24,000 years, then after 24,000 years, we would have half of it left, which would be 1/4. So after 24,000 years, one half-life which would be 1/4 kilogram, which is 1/2 of the original amount, remains. All right, let's try letter B. So letter B says, well, what about 72,000? So same idea. I'm going to plug it into this formula. So 0.5, 1/2, 72,000 divided by 24,000. Now I can type that whole thing into my calculator, or I can simplify the exponent first. That's kind of up to you. But we would end up getting a 3 here. This would end up being a 3. And so what happens is we get 1/16 kilograms. And so if you think about it, 3 half-lives have occurred. So we would have a half, and then 1 half-life would occur, and we would have a 4th, and then another half-life would occur, the second, and we would have an 8th, and then a 3rd would occur, and we would have 1/16 left. So 3 half-lives occurred, therefore we have only 1/16 kilogram left. Okay, we can also use exponential functions to model population. A 2010 estimate of population in Mexico is 111 million people with a projected growth rate of 0.994% per year. At this rate, the population P at T in millions can be approximated by this formula, where T is the time in years since 2010. Evaluate P at 4 and interpret the meaning in the context of this problem. So P at 4, we're just going to take 4 and plug it in for T. And whenever I do this, I get approximately 115. What this means is that since we're finding P at 4 and we're starting in the year 2010, we are talking about the year 2014. So in 2014, the population would be approximately 115, and since it's million people, it's going to be in millions. Okay, Please try P at 75, maybe pause the video and see if you end up with the correct answer. Okay, so I'm going to show my work. I am quietly showing my work here. All right, so it would be approximately 233 million in 2085. Remember, we're talking about how many years have passed since 2010. So P at 4 is 2014. P at 75 would be 2085. All right, I hope that helps. Have a great day.